Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 37. In this lecture, we'll discuss fluid dynamics. This topic is covered in Chapter 14 of our textbook by Surway and Jowett. Our discussion of fluids so far has been limited to fluid statics. In other words, we've been studying primarily the physics of fluids that are at rest. In this and the next lecture, we want to discuss fluid dynamics. We want to discuss the physics of fluids that are in motion. We want to understand, for example, the flow of gases and liquids through pipes and conduits. Now, before discussing fluid dynamics, I should make a disclaimer. Fluid dynamics is not yet completely understood. Fluid dynamics is a subject of cutting-edge research in physics. The governing equations of fluid dynamics are not yet completely understood, and therefore even physicists on the cutting edge of the discipline must make certain simplifying assumptions. These assumptions make the fundamental equations more amenable to solution. And we'll be doing the same thing in this course. Throughout our discussions of fluid dynamics, we'll assume that the fluid flow is quote-unquote ideal. An ideal fluid flow has four important properties that I want to discuss with you. First and foremost, we will assume that the fluids we're discussing are inviscid. Inviscid basically means the viscosity of the fluid is zero. You should have a vague idea of what viscosity means from your mechanics course. Roughly speaking, viscosity is the thing that tells you how thick the fluid is or how easily it flows. A fluid with a high viscosity is a very thick liquid and it doesn't flow very easily. Here are some examples of viscosity. Air has a viscosity that is almost zero. Water flows very easily also, and therefore its viscosity is quite low, almost zero. Olive oil is a slightly thicker liquid, so it has a higher viscosity. Honey, on the other hand, is a very thick liquid. It does not flow easily at all. There's a large amount of friction between the molecules, and therefore the viscosity of honey is quite high. The physics and the equations that we'll develop over the course of this and the next lecture will be applicable to air and water, but they will have large margins of error when applied to olive oil, and they are not at all applicable to honey. The fluids that we'll be discussing will also be incompressible. We will be discussing only fluids that cannot be compressed, or more precisely, fluids whose density is uniform. So we will assume that the density of the fluid is essentially constant throughout the flow. Now, air is actually quite easily compressed. You know this if you've ever tried to squeeze a rubber balloon filled with air. However, in our discussions of the flow of air, we will always assume that its density is uniform. So as air flows through a pipe or a conduit, like the air conditioning vents in your home, its density remains essentially uniform, so we can consider it as an incompressible fluid. We will also assume that the flow is laminar. Laminar flow essentially means that the flow is continuous and quite predictable. We will be assuming that there is no turbulence in the flow. Lastly, the fluid flows that we want to discuss will be irrotational. So there is no rotational motion or vortices in the fluid. A little more precisely, we can say that the fluid does not have any angular momentum. These four assumptions are essential. Without them, the equations will become too difficult and we will not be able to say anything that is meaningful about the dynamics of fluids. Now, you might be unhappy with these four assumptions. You might be interested in learning more about vortices, or you may want to study turbulent flow, or you might just be interested in the physics of honey. In that case, I invite you to solve the Navier-Stokes equation. The Navier-Stokes equation is the fundamental equation that governs the dynamics of fluids. To date, A general solution to the Navier-Stokes equation has not yet been found. In fact, in the year 2000, the Clay Math Institute proposed 7 unsolved mathematical problems, which came to be known as the Millennium Problems. The Clay Math Institute offered a $1 million prize for the solution to each one of these 7 problems. As of 2022, only one of the 7 problems has been solved. The Navier-Stokes equation remains one of the unsolved ones. So assuming that the fluid flow is ideal, as I just described for you, we can now begin our discussion of fluid dynamics. The first important concept that I want to introduce to you is flow rate. Volume flow rate in a pipe is the volume of fluid that passes through a cross-section of the pipe in 1 unit of time. Basically, volume flow rate is the amount of gas or liquid that is passing through the pipe or conduit per second. We'll denote volume flow rate using the letter I. The flow rate is equal to the cross-sectional area of the pipe times the speed of the fluid in the pipe. To have a concrete picture in mind, imagine a pipe. The pipe could be circular in cross-section as shown here, but it could also be square or any other shape. The important thing for us is the area of the cross-section of the pipe. So A refers to the area of this circle here in this particular picture. We will be assuming that the pipe is always completely filled with fluid. So we will not be discussing the physics of pipes that are only partially filled. The fluid might be moving rapidly or slowly through the pipe, but we will assume that the pipe is always filled to capacity. If you zoomed in on a molecule of the fluid, you would notice that it's moving from one point to another, and from that observation, you could figure out the speed of the fluid. A little more precisely, you could focus on a segment or element of the fluid and track its motion. As you do so, you might notice that the fluid element travels distance delta x in time delta t. From that observation, you can find the speed of the fluid. So the v here is simply delta x divided by delta t. The SI unit of volume flow rate is cubic meters per second. You might also encounter liters per second or gallons per minute, but the preferred SI unit is cubic meters per second. If a pipe with flow rate I is used to fill a container, then fluid volume in the container changes according to this equation here. So the volume flow rate is equal to the derivative of volume in a container with respect to time. For example, if you're using a faucet to fill a glass of water and you want to know how much water there is inside the glass after some time, you could use this equation to figure out the volume of water, assuming that you know the flow rate in the pipe. If the flow rate is constant, then this equation can be approximated as delta V over delta T. This is a rather useful equation because it can then be rearranged to write delta V is equal to I delta T. Knowing the flow rate I inside a pipe, you can figure out how much water will be in the glass after any given time delta T. The concept of flow rate is relatively easy to understand so long as the pipe is uniform in cross-section. However, realistic pipes often change their cross-sectional area as they become narrower or wider. We want to understand what effect this has on the fluid. So consider a segment of a pipe and imagine that the cross-sectional area is becoming smaller. We don't care too much about what's happening on the left or on the right. We only care about the fluid as it enters this segment and as it exits this segment. At point 1, the fluid encounters a relatively large cross-sectional area. At point 2, the fluid encounters a relatively small cross-sectional area. Throughout, we're assuming that the pipe is completely filled with fluid. What that means is that as the fluid enters this narrow region of the pipe, it must necessarily speed up. To better understand and quantify that fact, we need the continuity equation. Let's now derive the continuity equation to make that concept more precise. First of all, by conservation of mass, the mass that enters on the left side must equal the mass that exits on the right side. We cannot have water molecules disappearing, so in a sense, if 100 water molecules enter per second on the left, we need to have 100 water molecules exiting on the right. Furthermore, we are discussing ideal fluids, which means we're discussing fluids that are incompressible. What this means is that the density is constant or uniform throughout the flow, so we can say that the density on the left side at point 1 is equal to the density on the right side at point 2. These two assumptions essentially imply that the volume of fluid that's entering the pipe on the left must equal to the volume of fluid that's exiting the pipe on the right. This is essentially a consequence of the definition of density. We call that density is mass divided by volume. If the mass is the same and the density is the same at the 2 points 1 and 2, then the volume must also be the same. Now let's be more precise about the fluid volume. From our discussion of flow rate, we know that volume can be expressed as flow rate times time. Flow rate itself can be expressed as the cross-sectional area of the pipe times the fluid speed. What this equation is telling us is that the volume that passes through the pipe in some time delta t can be expressed as area times speed times time. Now, if we're talking about a pipe segment that changes its cross-sectional area, then we need to be more careful. We need to talk about the volume that enters the pipe segment and the volume that exits the pipe segment. If we want to talk about the volume at point 1 entering the pipe segment, then we need the cross-sectional area at point 1 and the speed at point 1. If we want to talk about the volume that's exiting the pipe at point 2, then we need the area at point 2 and the speed at point 2. Now, on the previous slide, I showed you that V1 must equal to V2. If we take these two expressions here and set them equal to each other, we arrive at the all-important continuity equation. The continuity equation tells us that the area on the left times the speed on the left is equal to the area times the speed on the right of the pipe segment. In some sense, the continuity equation is telling us something obvious. It's basically telling us that the flow rate entering the pipe segment must equal to the flow rate exiting the pipe segment. Think about what would happen if this weren't the case. Either the fluid would have to get compressed within the pipe segment, which is not allowed for an ideal fluid, or the pipe would have to be clogged, and we're assuming that our pipes are not defective in that sense. For us, the important consequence of the continuity equation is this: fluids flow more rapidly through narrow spaces. You can see that directly from the continuity equation. If the pipe is getting narrower, then the cross-sectional area is going down, and to maintain the equality, the speed must go up. And of course, the opposite happens if the pipe becomes wider. As the pipe becomes wider, the cross-sectional area increases and the speed must decrease. Let's end this lecture with a practice problem. A swimming pool with dimensions 8 meters by 4 meters by 2 meters is to be filled with 2 garden hoses with flow rates of 0.6 liters per second and 0.8 liters per second. How long does it take to fill the swimming pool? Now we can start this problem by calculating the volume of the swimming pool. That should be easy because the dimensions of the swimming pool are given to us in SI units. By multiplying 8 by 4 by 2, we find that the volume of the swimming pool is 64 cubic meters. So to fill this swimming pool, we need to provide 64 cubic meters of water. Now we are using 2 hoses to fill the swimming pool, so what we really need is the total or net flow rate. We can find the net flow rate easily by adding I1 to I2 to find that the net flow rate is 1.4 liters per second. So the 2 garden hoses working together can supply 1.4 liters of water every second. Now note that the liter is not an SI unit, so we need to convert it to cubic meters. We can do that using the factor label method. We need to know that there are 1,000 liters to 1 cubic meter. Dividing 1.4 by 1,000, we find that the net flow rate is 1.4 times 10 to the minus 3 cubic meters per second. Now that we have the volume and the net flow rate, figuring out time is relatively easy. Recall that the flow rate is equal to the derivative of volume with respect to time. When the flow rate is constant, we can approximate this as delta V over delta T. By rearranging this equation, we find that delta T is simply equal to delta V over I. Here, delta V refers to the total volume of the swimming pool, which we have already found. Plugging these numbers into our calculator, we find that the time required to fill the swimming pool is 45,714 seconds, which is approximately 12.7 hours. And that is the end of this lecture. Thank you for your attention.